Today I am going to be speaking for the final EiCLaR podcast, and I have the great pleasure in introducing you to Azariel Ruiz-Valencia of the National Centre of Scientific Research of Lyon. So welcome, Azariel. Thank you for giving me your time.
Thanks to you for this opportunity.
So today I wanted to, like the other EiCLaR podcasts, what I'd like to ask is a few questions about who you are, where you've come from, because we have a huge variety of backgrounds for the consortium. So could you tell me a little bit about yourself, please?
Yes, of course. I think something that EiCLaR has is this, as you said, this broad, different characteristics of a human, all the different origins of the people. So I am from Mexico. I am from Mexico. I study as engineer in the south of Mexico. And then I have the opportunity to come to France to make my PhD. I made my PhD in the south of France, in Montpellier. And then, well, I have some experience as a postdoctoral researcher, in which I always, in all my formation, I have always this experience with the environment. I have this awareness and how we can improve the environmental, the environment in general. And I always did it with the help of the different microorganisms. So I am a very biological bioprocessing engineer. So that was one of my motivations to work with the life with the alive microorganisms and to do something to improve the environment.
Great. So you did your undergrad in Mexico and then you had the opportunity to transfer to France. So how was that mechanism? Was that through a sponsored system, or how did you get from Mexico to France? Was it a Erasmus, or how did you
Oh,
come to?
there is a program, it was through a scholarship. There is a program that is called, the organization that is called Campus France. And they have an agreement with the Mexican government, and they have some scholarships for people to come from Mexico to study a PhD in France. So I took this program, I applied to it, and I have the opportunity to be accepted. And I focus, as I told you before, for this thesis, I make a process to transform the CO2 into a compound that is called formic acid with the help of a bacteria. And this bacteria is able to do this conversion naturally. And we also use the electrons that we cut from the environment. So it's something that we developed during my PhD, and I had the opportunity to apply for a process for a postdoctoral research 2 years more. So it's something that I would like to highlight. That is, I have the pleasure to develop this process in the south of France.
Oh, fantastic. So how long? So from your PhD, what sort of is it a 4-year PhD you did in France, and then you've done your postdoc for a couple of years, or just to give people an idea of how long you've been in education?
Okay, actually, my PhD was 3 years, 3 years and a half, because we have this discovery. So we saw the need to patent it, so we did it, and that took us another year. I made my PhD from 2015 to 2018, but finally I made the final defense in 2019, in March of 2019. Then I stay 1 year more in this. It was a mixture between the postdoctoral and engineering status, because I end at mid June in 2020. And it ended because of COVID. So it was one of the main reasons why this project end, because this all the research projects suffer from this cut of fundings. So yeah, we didn't go further in the project. And then at the beginning of 2021, I was recruited into the EiCLaR project to be part of it. And since then, I am being being in the work package 2 of this EiCLaR project.
Fantastic. So you can see your of the different people that we have been interviewing for the EiCLaR project, we have the coordinators who have lots and lots of years of experience, to the postdocs who are supporting the project to move the science forward. So we're showing that we have got lots and lots of different age groups and people from all across the world collaborating on this project. So your role within the EiCLaR project, you're on work package 2, you said. So
Yes.
that's looking at the bioelectrical chemical remediation. So the whole project is looking at developing 4 different technologies, and you're working on one of the work packages looking at bioelectrical chemical remediation. Is that correct?
Yes, it is correct. Actually, in this work package, we have 2 different technologies. We have the bioaugmentation that I guess that you have also discussed about it with
Yes.
I don't remember with Stefan, I guess, or
No,
with
his
Andreas.
Andreas, yes.
Okay. So yes, I'm participating in this part of work package 2. We have the bioaugmentation and we have also the bioelectrochemical remediation. So the link between these 2 different technologies are the microorganisms. As you may know at this moment, the core, the heart of the project is all the biological inputs that we study. So for both work package, I have been in charge of do the analysis of microbial all the microbial analysis. Oh, I could say the microbial communities. Yes, that's a better word. So in both work package, I've been in charge of the microbial communities to study the microbial communities in order to see which one are the microorganisms that are arising or taking the lead into the degradation of the different pollutants. In the case of the work package 2, they are working with chlorinated compounds. So we are studying which chlorinated compounds are inducing the presence of which microorganisms. In the same way, in the bioelectrochemical remediation, we have some bacteria that have this capability of transfer electrons from one solid surface to be able to degrade some compounds or make the reverse operation. So in both work package, I am doing kind of the same thing, studying microbial communities. But in the technology of bioelectrochemical remediation, I am also in charge of developing the process and to take it into a bigger scale, meaning that we started in the early steps of the project. We studied in a very small scale, like in a little flask, with a lot of we put it polluted soil indeed, and we saw that by applying or by placing an electrode in the middle of the soil and a cathode and another electrode outside of the soil, we can improve the degradation of these compounds. Actually, this technology, the bioelectrochemical technology, it is based on the principle that, well, it is to overcome some difficulties that the natural attenuation is having. In natural attenuation, when you just let the contamination in the soils, in the salts, um, you have these different communities of bacteria that can degrade the pollutants. But in a given moment, the lack of they can all the let's say in simple words, it's like they are eating a lot of food. But in this with when they eat a lot of food, they don't have anything to put all the rest of the food. And in this way, it's the electrons. So we need some electron receptors to place these subproducts of the degradations in some place. Usually, the main electron acceptor is the oxygen, but under the soil we have no oxygen. So we need to put another chemical compounds to increase this again to feed this process. But this is not a new technology, the bioelectrochemical technology, but the application of this in polluted soils is very recent. So we put these electrodes and some bacteria, in this case that we call them electroactive bacteria, they are able to capture all these electrons that they were discharged by other bacteria. They take it and they put it into the electrode. And the electrode, this is a conductive material. It can be transferred all over the surface of up to the surface of the field, and then there it can be reduced with the oxygen that is present in the atmospheric air. So it's more or less like a snorkel-wise technology where the bacteria in the bottom of the soil can breathe easily thanks to this electronic transfer with the help of the electrodes.
So yeah, snorkel is a very good way of describing how you are stimulating a large column of
Exactly.
material which you wouldn't have been able to stimulate without the electrodes giving the right conditions. You're making the conditions better to be able to treat the contamination,
Exactly.
which is really important, because often the different contaminants will sit there and the bacteria will use what they can and then stop. They won't be able to treat more.
Exactly.
So you are looking at this. So you started in the column side, the smaller scale, and then you have used the knowledge that you have gained to move to larger scale onto sites?
Yes, it is actually we have as part of the project, the EiCLaR project, we have reached to some partners, and we have a site in Watford that right now is running with these electrodes, and we are going to see in a few days from now if how they perform. Because the other interesting fact about this is we can measure how many electrons are being transferred, because it's a current. Since we have a flux of electrons, we can call it a current. And if we apply a current meter, we can measure the current over the time, and we can see how much of the degradation has been taken place in those sites.
Right.
So it's a nice way to accelerate the natural remediation, and also a way to measure how fast this natural adaptation is occurring. And we can we are very excited to get back to the results and get the information as soon as possible, and see how this technology is performing in a polluted site.
Yeah. So this is in the UK, Watford in the UK.
Yes, exactly.
Yes. So you're using it in real. So where you are measuring the electrical current, are you able to do that remotely, or you have equipment on the site?
So far we are doing on site because one of the things that we didn't take into account is like the lack of electrical current in the site. So we need to be inside to recover the data. We had the opportunity to have a device that can transfer the data via satellite. But we don't have electrical current in the site, so
Right.
yeah, we need to just go and recover the
So
results.
that is something to consider when you are looking at remediation, is looking at the site conditions. So having an electrical, source to be able to plug into is often something that is overlooked if sites are derelict or redundant. The electrical sites are turned off. So yes, that's
Yeah,
something to consider. But you can gather the information by visiting the site and downloading the information. So
ex
that's
exactly. Yeah. So yes, we are going to. Um, we found some technology that is able to capture this all the current that is occurring during the last 3 4 months more or less, and then we can I have just to go plug it in with my computer, download it, and then I have the opportunity to analyze how well it did perform this technology based on the size of the electrodes and the yeah, based on the size of the electrodes.
hmm. So in your view, what would be the potential benefits of the technology are to speed up the remediation process and to treat a deeper level of contamination than would have previously been treated. Are there any other benefits that you would like to sort of identify for the technology?
I think as we are discussing now, it's the two main advantages of this technology is one, the acceleration of the natural attenuation
Mm,
because it is going to happen faster, and also as you mentioned, it can go deeper. So depending of the deep of the wells that are installed, we can go very deep, and we're going to accelerate. We haven't measured how fast it can be in a real site, but it's something that we are willing to discover soon. And that's the first advantage. And the second one is that we can also measure the degradability of the compounds in the site. So, for example, if we see that we have a very low activity in the site, we can do something to overcome this slow path. For example, if we see that we have a slow activity, we can add some bacteria or we can add some compounds that maybe help the bacteria to increase the degradation rate. So it can be for monitoring a site and also to degrade it. So it's an indicator and that is very accessible for a site, no matter where it is. And yeah, so for me, those are the main advantages of
mm.
this technology.
Brilliant. And so for the next stage of this technology, where would you like to see it going, or what would you like if you had what we would say a magic ball to sort of look into the future? What what would be the next stage that is beyond the EiCLaR project, but what would you like to see the next stage of development?
Actually, the next stage, I think I will be because since as I in the project we are mostly microbiological or ecological or geochemical people, yes, and communications. But I think that something that can improve this process is having someone with expertise in materials to have a material that has best support for bacteria, that bacteria can install themselves very quickly. And so we can design something that is easily we can find in the commerce in the future. That's the future I am shaping into it, like in the next years commercialize it. Yeah, that would be my have some kind of big electrodes that you can put in the site, and yeah, accelerate the ton of polluted sites that are in Europe so far, and see what other process are helping this system. For example, maybe it can help not only with hydrocarbons, but also with chlorinated compounds, or also with to capture different pollutants that we haven't identified, and see how this perform over time. And maybe, yeah, we can, yeah, if I dare to dream, you only dare to dream, help with the PFAS remediation.
Mm.
But so far, that's just a dream.
Yes, no, I that is the thing, is looking at opportunities of treating contaminants that aren't necessarily being treated at the moment. So stimulating, trying to treat things quicker, which will be more effective, more cost effective, which will improve communities globally. I'm guessing also trying to make things as cheap and efficient as possible. So it means that people will start to look at other sites that maybe they've thought are too difficult to deal with. But if you can add new technologies and cheaper technologies, then that will improve things for the good. So I would like to thank you for sharing your thoughts on all the work that you are carrying out, from the biological and the monitoring and all the knowledge that you have shared with us on this conversation. So I'd like to thank you for your time, for giving your knowledge and sharing what it's like being a postdoc within the EiCLaR project. And it's been a delight speaking to you. Thank you, Azariel.
Thank you very much.